Morning, everyone. Can we ask a bit of silence, please? Thank you very much. We are back to the seminar series of IvS after this annoying holiday last week. I'm pretty sure you all wake up last Thursday thinking, oh my God, no seminar today, and blah, blah, blah. But welcome back. We have a seminar today that will be given by Olivier. So he is with us for ages now, I think. He did his bachelor and master at KU Leuven, and he is doing his PhD with us now. And today he will be talking about massive stars, more specifically B-supergiants, and even more specifically about mass loss and clumping. Is that right, Olivier? Aha, I'm not prepared. Anyway, the floor is yours, Olivier.
Thank you. Okay, so indeed I'll be talking about mass loss rate and clumping factors in B-supergiants. Quick overview of what I'll be talking about. First, I'll give an introduction on massive stars and their winds, how I look at them, a bit of the theoretical background that you might want to have before we dive into it. Now we'll be talking about how we fit big parameter spaces. So what I did is, I didn't just look at the models or anything, I actually looked at observations, looked at LMC B-supergiants, compared those observations to pretty high parameter space models, and we're going to talk about how we deal with fitting these big parameter spaces, because it's always a hassle if you have like 18 parameters running around to fit them all at once. Then we'll talk about actual results, look at how the clumps actually behave observationally in these winds, and then we'll also look at the mass loss rate and compare those to the actual theoretical models we have, and then some consequences based on the difference we see there. And spoiler alert, there will be some difference there. First off, this is the nominal starting slide for every massive star talk, I feel. It's just massive stars. What do we mean by this? We mean everything that's above 8 solar masses, basically everything that at the end of its lifetime turns into these sort of exotic neutron star black hole kind of objects. But the reason I'm most interested in it is not really this stage, but more these stages where you have very high mass loss rate that is usually radiation driven. That means that it's a very specific type of wind that I'll get back to later, how they work exactly. Now, why do we care about massive stars? Because they aren't really that numerous compared to their low mass counterparts. We care about them to some extent because they have very hard feedback on their environment, both physically, because they have UV radiation, they ionize the region around them, but also their winds actually are so strong that they can dominate the region around them as well, and then chemically, because they produce these very heavy metals, and then later throw them into the galaxy due to supernovas, but also due to their winds. Okay, so quick overview of mass loss in stars. First off, you have solar-like stars. Very different type of wind than I'll be talking about. It's a pressure-driven wind. It's the pressure in the hot corona that is high enough to actually push out enough material or actually escape the gravitational pull. This usually results in pretty low mass loss rates. The sun, for example, has something of 10 to the minus 14 solar masses a year, if I'm not mistaken. So very, very low mass loss rate, but reasonably mid to high velocities. A couple hundred kilometers a second is logical there. AGB winds, totally different kind of wind. There you actually get material far enough away from the hot center of the star that is able to form dust in some way, and then this dust gets driven by actual just radiation pushing on it, and that just escapes. That gives you high mass loss rates, 10 to the minus 7, something along those lines, but it gives you low wind speed as well, usually a couple tens of kilometers a second, if I'm not mistaken. Then we get to radiation-driven winds with the massive stars, the thing I'll be focusing on for the rest of the talk now. And here, it's also radiation-driven wind, but the way it's pushing is completely different than with the dust. What is actually happening is the light is getting caught by the spectral line transition. So let's say you're an atom, you're an hydrogen atom because it's the easiest, and you have some sort of line transition, right? You're going from, I don't know, Lyman alpha or something, and you have a certain specific wavelength that you can absorb. And that means that you can absorb that specific wavelength, you get pushed a bit forward, it's only a slight bit, but now you have a slight velocity compared to the actual star itself. So now you're actually blue shifted, so you're sensitive to a slightly different light calibration, to a slightly different wavelength. So you can now collect that light from the continuum and get pushed forward even more. And this happens again and again and again and again until you actually escape the gravitational well and you just kind of get pushed out. This results in not only very high velocities, on the order of thousands of kilometers a second, 1,000, 2,000, 3,000 kilometers a second. Terminal wind speed is not unheard of, actually even observed, and usually pretty high mass loss as well. 10 to the minus 7 to 10 to the minus 4. 10 to the minus 4 is definitely on the very high end, but 10 to the minus 7 is something we see quite regular, definitely in these B-supergiants. Now, these massive star winds, these radiation-driven winds, have some natural clumpiness to them, some natural stuff going on in two ways. Once you have the turbulent surface layer, subsurface layer, where the wind actually gets launched itself is not completely static. It's not like a nice hydrostatic layer. There's some stuff going on. So when it gets actually launched, it kind of transitions this unevenness into clumps into the wind. And there is another thing called the line deshadowing instability, which is a very specific thing to radiation-driven winds, where if you listen to my explanation before, you have a certain element. Now let's imagine that you are out of sync with the elements around you. So you're moving slightly slower, let's say, than everything around you. Because you're moving slightly slower, everything closer to the star is actually already moving your speed, because they should follow this sort of beta law. So they're already moving your speed, which means that the light that you should be absorbing, because you're Doppler shifting, is actually already being caught by the parcels in front of you, which means that now you're actually moving too slow, which means you're not catching any radiation, which means you'll slow down further, which means you'll back up into everything else, and that naturally forms some clumping, because this is a runaway effect. Because as you get slower and slower and slower, you get less and less and less radiation, because it all gets caught by the clumps before you. So you get some natural clumping going on there. Yep, okay. Okay, I've talked a lot about these radiation-driven winds now, but why do we actually care about them? Why all this explanation to these radiation-driven winds? Why should you care as a person who's not really interested in the physics behind these radiation-driven winds? Well, in massive stars, definitely the very massive end, this mass loss rate becomes so significant that if you do small changes to the actual mass loss prescription, you can end up with completely different stars. What we did here is what Björklund did here is he had a 60 solar mass star, very basic model in MESA, and ran 2 models from it. One's with his own mass loss prescription, which is a slightly lower mass loss prescription, and one's with the Vink prescription, which is the baseline for MESA. That's like if you start up a MESA model and you have winds in there and you haven't looked at what you're doing, you're probably using the Vink rates. Okay? What you see in the end is that if you use the high mass loss rate prescription, the Vink rates, you end up with something that is probably like a Wolf-Rayet-like star. 23 solar masses at the end of helium burning, you end up with something along those lines. It's in the correct spot for a Wolf-Rayet star, just like the mass you would expect. But if you actually use the low mass loss prescription, you end up with something that's more than double its mass, and it acts completely different. It's not at all a Wolf-Rayet star. It's actually very hard to form these Wolf-Rayet winds or these Wolf-Rayet stars if you start with a lower mass loss rate prescription. And so this will also have an effect in the actual final black hole mass you look at the end, because if you're Wolf-Rayet, if the end mass of your object is different, then once it goes supernova and you get a black hole, it will also change the masses. And with the recent addition of gravitational waves, we actually have a handle on these masses of black holes as well, and we can see that they do not align with what we expect. One of the reasons could be that maybe we're not looking in mass loss rate of these massive stars in the correct direction. Maybe we're overestimating them a bit. So this is just to show that a slight change in mass loss rate prescription can give you a very different end results in your objects. Now, what was the actual difference here between these 2 prescriptions? Because I kind of left it vague. I said a high and a low one. You have a high mass loss rate prescription, a low mass loss rate prescription. Well, I plotted them here for you. So for one specific luminosity and mass, here I plot the mass loss rate for a specific temperature of that star. And you can see that the high mass loss rate prescription, as I call it, the Vink prescription, has this feature going upwards, while the Björklund prescription just monotonically goes downwards. Now, what is happening here? This is what we call the bistability jump. The bistability jump is believed to be an increase in mass loss rate because iron 4 reionizes into iron 3 here around this temperature. Now, if you remember what I said before, radiation-driven winds, they actually push against these line transitions. So if you add an extra electron to the metals you're pushing against, you would expect that you get a lot more line transition, a lot more possible line transitions, so the wind could become more efficient. So there is some logic to it there. But the question is, does this jump actually exist? Because more recent modeling do not find this jump at all. They just see a monotonic decrease. So is it there? Is it not there? Well, we're going to try to figure out, but just keep in mind that if you're running MESA models right now, again, you are using this jump, just so you know. It is in there. If you go low enough in temperature, around this 25 kilokelvin range, you will encounter this. So that's the goal of what I'm going to talk about today. I'm going to look at actual observations, try to determine mass loss rates, and see if we find stars clumped around here doing this jump upwards, or we find stars that are low down here. Now, to do this, I need spectra, and my spectra come from the XShootU collaboration. They provide me with optical and UV spectroscopy, and my sample is in histogram form and very rough temperatures plotted here. So you can see, for instance, I have 3 B-supergiants here at around this 30,000 Kelvin range, and this is like the distribution of stars. So my sample should cover this range enough to see if this jump is real. Because the jump is so big, this is almost 2 orders of magnitude that we're talking about, it should be pretty obvious if it's there or not, even if I get pretty big error bars in the end, which actually is pretty fine. Now, I'm not the first person to look at this and be like, this looks a bit odd, like this huge jump, how do we know how big it is, all that stuff. So there are people before me who tried to do as well, Marco van Poels and Rebio Diaz, and they had one small disadvantage that I am able to resolve, which is the fact that they cannot take into account this clumping I talked about before. This clumping due to the subsurface layer, this clumping due to the LDI, they cannot take it into account at all because they only had access to optical, or in Rubio Diaz's case, radio data. And the problem with that is that if you model the typical line you use to determine mass loss rates is the H-alpha line in optical, and if you only model that one with a specific clumping factor and mass loss rate, clumping factor, by the way, is how we define how over-dense the dense regions of the wind are compared to the average. So if clumping factor of 40 just means that the clumps are about 40 times more dense than the medium. So if you plot this H-alpha line for a specific star with this clumping factor, this mass loss rate, it looks something like this. My UV line looks something like this. But now if I change the clumping factor and the mass loss rate and tune it a bit, I can get out a line that looks, at the peak at least, significantly similar. And this makes it hard to disentangle this clumping factor from this mass loss rate. So usually what you have to do if you only have an H-alpha line, you either assume a certain clumping factor, so you say clumping factor 10, because that is the logical number to use for some reason, or you assume a smooth wind. You say, we cannot say anything about clumping, so let's just make it more simple and assume it's smooth. But if you have UV resonance lines, like I do in my sample, you see that the difference here, even though this is still fine-tuned to be sort of the same, the actual UV resonance lines do change quite a bit. The absorption troughs become bigger, the emission trough here becomes higher as well. So the idea, at least, is that if we have these UV resonance lines, we're able to break this degeneracy between clumping and mass loss rate, and therefore get out more accurate mass loss rates and no longer what we would call upper limit estimates, assuming a smooth wind. Okay, cool. So I talked a bit about this clumping and how some regions are more dense than other regions, but the problem with this is that it's inherently a 3D type of effect, because you have your clumps, and next to it stuff needs to move, and the clumping actually gets caused by this turbulence at the bottom, but then in 1D, how do you do turbulence? So that's all kind of 3D effect that we're now trying to put into 1D. Now, you could just say, okay, just use 3D models to make your spectra, and then compare those to observations. Well, the problem with that is that 3D models take a long time. So usually for one model, you take more than 10 hours, and then you haven't even computed spectra from them. You just get out a cube like this with certain mass and velocity and density and stuff like that, and temperature, but you don't actually have spectra out of it yet. To produce spectra out of it later, you need an additional time to actually do that. That's actually something we're doing in the group right now as well. We're actually looking at these 3D models, trying to optimize them, trying to make them better, trying to get spectra out of them, but we're a long way away from actually using them for fitting, because you just need a lot of models for fitting, and I'll get back to why you need so many models for fitting later. So what do we do instead? We look at the results out of this 3D method, or these 3D models, and then try to parameterize the behavior we see into 1D. And you can kind of get 3 parameters out of the 3D simulations and put those into 1D to try and simulate this clumping effect. This is the clumping parameter, the one I talked about before, telling you how dense regions are compared to the average. The interclump density, telling you how much underdense the non-clumps are compared to the average. And you have something called the velocity filling factor, which tells you how much of the velocity space you're filling. I'll get back to that. First, clumping. Clumping, again, in this simulation caused by turbulence present at the surface. This is actually of a Wolf-Rayet star as well, which is slightly different, but the same idea is still present. What you see here is this density map with relative density. So you can see that the dense regions are about 10 times more dense than the average, and the underdense are about 10 times less dense. It's like what you see here, you see the clumps moving around, and you see that's clearly not a smooth outflow. So we're trying to simulate this, but then in 1D. How we do this is we make a 2-component medium in Fastwind. Fastwind, by the way, is the synthetics spectra maker that I use. You make a 2-component medium of the clumps and the interclumps, and you give them a sort of factor, like the clumping factor and interclumping factor, to tell you how dense or underdense they are compared to average. And then to get your ionization structure out, because we want to know what ionization level silicon is at every radius, you base that on the average of those two, a weighted average. It's a bit more complicated, but it's fine. Then this compares actually slightly differently to other codes used right now, and I think this is an important point. This addition of interclump density is actually quite rare in our field. Usually, people just assume that most of the wind mass will be in the clumps, because they're assuming to be so much overdense compared to everything else. Everything is in clumps anyway. Why care about modeling the interclump? Just put it void. Put it to 0, don't care about it, and we're done. That could be an option, but we'll get to back in the results section later why I think that might be a slight issue to that. Okay, and the final thing is this velocity filling factor, or the velocity porosity. What is plotted here is a specific section of such a Wolf-Rayet model where you can see outflows, but we've removed all the mass or all the outflows that's not moving at this specific velocity, so in between 990 and 1,010 kilometers a second. So this is the only piece of stuff moving at this specific velocity. And as I talked about before, this velocity is really important because this Doppler shift you get makes sure that you absorb the correct wavelength. So if you're not on the correct velocity, if you're not having the correct Doppler shift, you cannot absorb the photons you should absorb. So if you look at the top through this effect, you see that as I am light of a certain wavelength, I can just pass by every clump. I just don't get absorbed because there's a lot of holes here. If I'm in the wrong place, yeah, I'll get absorbed by the material, but in between there's enough space for me to just kind of pass through. And this light leaking effect is what we call velocity porosity. So just the effect that because not everything is moving at the exactly same speed, there is some room to escape through it. Okay, so I talked about a couple parameters right now. I want to add a lot more, because we need temperature to be well defined, because we need to make this plot with mass loss rate and temperature. That's the end goal, so we need a good temperature. To do that, we also need a good log G, and we need a good helium abundance, because the helium abundance, well, the helium lines is what defines our temperature usually. We want CNO abundances to be defined, because there's a lot of CNO lines that are wind sensitive, and we want them to behave well as well. So we need CNO abundances. Then I clumped all the broadening effects that you usually talk about in spectroscopy, like micro, macro, and rotational broadening, and I just all clumped them into a rotational broadening effect, which I call max V sin I. This is not an actual rotational velocity, this is everything put together. So no micro clumping, no micro broadening, no macro broadening. There's just like this one effect of rotational broadening that is going to be a proxy for all the broadening effects, because we already have a lot of parameters, and I'm trying to reduce them at least a bit. So that brings us to 7 stellar parameters. Then we have 9 wind parameters. Obviously, we want the mass loss rate. We want terminal wind speed, the speed of the wind at infinity. We want the clumping factor, interclumping factor, and velocity filling factor, so how much of the velocity space we're filling. Then we want to define where the clumping onset is, so where the clumps start to form, and when they actually are fully formed, because there is like a forming radius there that we need to handle as well, so we need those 2 parameters. Then we have the beta parameter. This is the typical beta parameter of the beta wind, so just telling you how fast your wind is accelerating. And then we have wind turbulence, just turbulence in the wind. And then we have X-rays. I haven't talked about X-rays yet, so let's quickly explain why we add X-rays. If you have this clumpy medium where stuff is moving around, and you have one clump that's moving significantly faster than a clump ahead of it, it can just bump into it. And when this difference in velocity is high enough, you could create a heating effect that actually is strong enough to create X-rays. And to simulate that, we add 2 more parameters, which is the volume filling factor, but now for the X-rays, telling you how much of the volume is actually emitting X-rays, which is usually really low, it's less than 1% usually. And then U infinity, which tells you what the difference in velocity between those 2 blobs are. Now, how do we deal with 18 parameters? How do we fit 18 parameters at once? It's not easy. What you want to do is you want to look at your layout of your chi-squared in this case, or whatever loss function you decide, and you find the best one. Usually it's a dip, but I just flipped it around, and here it's the top of the hill. So we want to find the top of the hill. If Steve wants to find the top of a hill, he has a couple of different options to do that. He can either just look at the ground where he's standing right now and decide, okay, this hill is going upwards, let's follow it. And as long as it's going upwards, I will just follow it. And this is the basic idea behind gradient descent. Steve will just move up until he can no longer move up, or everything around him no longer moves up. So he just decides, okay, if nothing around me is moving up anymore, I'm probably at the top of the hill. Does this work? Yeah, it usually works. If you have pretty simple parameter space, a pretty simple chi-square distribution, this works really well, because it's very fast. You just need one core to do it. It's super efficient. The problem with it is, how does Steve know that he's not at the top here? Because this hill looks a bit flat at the top, right? Over there is nothing moving down. So Steve could decide that he's just at the top here. So how do you get around that? Well, there's a couple different ways to do that. A very popular method is the MCMC, or the Monte Carlo Markov chain method, where Steve gets around a lot of his friends and he just drops them on the hillside. So he just puts them everywhere randomly. He just tells them, go set up somewhere, but once you're there, take a random step in a direction. Just go somewhere. Take 20 steps in a direction, and if your spot you're in now is better than the spot you were in before, stay there. So they do that, they move to a random position, and now they're there. And in theory, this could work. If your random step is big enough, you could overjump these local minima and actually get to a real top. Slight problem, or not really problem, but caveat with that, is that the walkers, they don't communicate with each other. They're just going their own way, and right at the end, when everybody feels like they're kind of in the spot where they should be, they come together and they discuss who was actually at the top now. And this works. This can, in theory, work to find your your global optima. This is, again, not guaranteed, but due to the random motion, there's a reason to expect that you could. But you waste a lot of computation time with people like the yellow guy over here, just kind of being stuck in the middle of nowhere, and everything around him is quite low. And he keeps putting random steps, but he's not really going anywhere. To resolve that, we can do something else. Now they're in a different hillside because I wanted a change of pace. But here we put Steve and his friends again, and we just drop them with a helicopter on a random spot. We don't make them walk there, we just put them somewhere. And we make them note down how high they think they are. So they make them note down. And at the end, we all gather them together. And then we say, OK, to the guys who are over here, you are way off. Just stop looking over there. And they redistribute them. So we just remove those and go to somewhere your friends were that was a lot higher and clearly a better position. And then do some random move again. So this is the same as the MCMC from there on. Just move randomly again and just put yourself somewhere. So that's what they do. They move to a random position, but you immediately get away from these clearly dead spaces. That's the idea anyway. And due to the random movements that you induce, you should still be exploring the whole parameter space and should still be finding these optimal fit values in the end. And this is what we do, or we try to do, to find these global fits. Now, I've been talking about this walking metaphor because that's the easiest one for MCMC, but genetic algorithm, the name itself kind of gives you a hint to what it usually uses the metaphor for, and that is the evolution of species, right? So how it is usually explained, and I'll do that on the hand of the actual code I'm using, which is called Kiwiga. How Kiwiga works is you make this random distribution, you make Steve go to his random positions with his friends, and you make the synthetic spectra using phosphorus. Then you compare that to the observations, so you get a chi-squared value out, and you look at which were doing well, which were doing not well, and you decide some sort of cutoff there, which are doing good, which are not doing good, and now you mix their parameters around. And this is where the genetic part of it becomes clear. You just mix their parameters around a bit. So you take the effective temperature of one, the log G of another, and so on and so on. So you make, in effect, children of the generation before it, and then you allow for some mutations to happen. And these random steps, this is what, in theory, should get you out of local minima, or hopefully gets you out of local minima. And then you just repeat this until we are happy with the end results. Now, we've been talking about these models a lot and so on, but let's look at what this actually means in practice. What do I actually need to do? Well, to run Kiwiga, I need about 50 to 70 generations to get good 18 parameters for one star. One generation takes about 100, well, it's exactly 107 models, which means that we're about 6,000 models in when we get to the end. 6,000 models is a lot of models. If we want to do that in 3D, 10 hours a model, we're looking at 60,000 hours. It's way too much, because those 10 hours is already using multiple cores. So it's really a lot of computation times. So that's another clear reason why we cannot use 3D models. It's just a computation thing. We just are not there yet. But if we use fast ones, which is a lot faster, it takes about 45 minutes on average for a model. So then it only takes about 190 days to compute all my models, which sounds insane, but they only use one core. So if I just parallelize it, I use 107 cores for each of my generations, meaning I use one core a model. It only takes about 2 days on a supercomputer to run. This is still a large computation load, and this is the reason why this hasn't been globally done yet, because it's just a lot of computations, but it is slightly more efficient than the MCMC. We actually avoid computing a lot of redundant models by not using MCMC. And at the end, just like in MCMC, it has the same advantage that we get global fits at the end with global errors, meaning that the error bars we get take into account all the degeneracies with all the other parameters, because there is no splitting of the parameters and looking at each fit of the parameters individually. They're all global. Now, what did we do before we had the computation power to do this? Well, we did something called by-eye fitting, where we looked at a spectra, like physically look at it, put it on top of an observation, and look at, OK, if we up the temperature slight bit, then we're probably going to be a bit closer, so let's do that. And then they do it again, but now they're tuning the mass flow rate, and do it again for other parameters. And there's this whole strategy around doing this as efficiently as possible. And in the end, you can get a decent fit. You can get good fits even, like maybe even better than you get with the Kiwiga in the end, because you could be in a local minimum with the Kiwiga method. You're not sure that you're out of it still. But the problem with this is, what do you do at the end with your end result? Now you have a best-fitting product, but what's the error on this? You just decided that this was the end point, right? There's no real reason for you to stop. You haven't explored the parameter space, and exploring the parameter space is super expensive. You were trying to avoid that. So how do you go to errors from here? Error estimates are super hard to do if you do by-eye fitting, and it's still being done with codes like CMFGen and Power, because they take a long time to run again. These are, again, very slow models, even though they're also 1D, but they do some stuff more complicated, and FastWind does it, so they're still really slow to run. OK, cool. This is the generic output you get out of Kiwiga. What you see here is the spectra you get out. So it's 3 different stars. You have the observations in black, and then the best fit in the dark green line. And the light green shade gives you the 1 sigma region that, around it. And in general, they fit reasonably. There are some lines that are not fitting perfectly, but in general, we get out reasonable fits. Now, this is fun to look at, but the actual gold of the GA method is this. What you see here is, on the x-axis, you see the mass loss rate, so over the entire mass loss rate parameter space that I looked at. And the x-axis and the y-axis, it is 1 over reduced chi-squared. So it's basically the higher you are, the better this model specifically was fitting. So every sphere, every dot is a model I ran with different parameters. None of them are repeating, although mass loss rate might be repeating, but one of these older 17 parameters is different. And what you can see here is that you get a well-peaked behavior where this region is like the good fitting models. Now you can do some statistic method to define how far below that maximum point you should define your error bars, and you get global errors out. And again, this is taken into account all the generacies, everything. This is just the error on mass loss rate taken into account everything. The color, by the way, actually represents how far in the generation we are. So the bluer the models, the older the generation. And here is also some neat thing you can actually see from this plot, that even in the newer generations, these green dots are still exploring, still going out in really far random walks to see if they cannot find a better fit still, even though they're clearly already at some sort of pretty good fit here. They're still exploring, and this jump is not defined at the beginning as 1 point, but it's just a Gaussian, so at the end they can still make jumps over the entire parameter space, which is part of the strength of this GA. Okay, that was all the introduction. For now, get to the results. Some of the results I got out of the actual GA fitting for the sample. So here's the sample. These are all the B-supergiants I fitted from the XShootU collaboration, and I just plotted them on the HR diagram. And the color I used to show you mass, the spectroscopic mass I get out. This is without errors, obviously, because it's difficult to show errors on the mass, at least. This is without errors because it's difficult to show errors in a color bar. But just to give you an idea what the masses are that we get out. And you can see that the masses range from 15 to 45, more or less, and that most of them are like past the main sequence. This is the main sequence, and you get like in this jump region. Okay, and already here you can actually see that the temperatures are pretty well defined. The errors on our temperatures are not too big, which we're happy about, because that's one of the things that we need to get correct. The main thing we're going for is mass loss rate and temperature. Okay, first result, real quick, is thermal wind speed. This is something I talked about in the beginning. There are a lot of people interested in this sometimes. What you can see here is the thermal wind speed over the effective temperature. I always plot effective temperature from high to low, because that's the way bistability jump is usually plotted, and I want to keep everything consistent, so that's why I'm doing it like this. What you can see is that there's a really linear behavior in the thermal wind speed. This is not really unexpected. But what is expected is that the color bar on this doesn't seem to influence that much. The color bar I haven't really spoken about yet, but this is gamma E. What is gamma E? Gamma E is telling you basically the radiation acceleration over the gravitational pull against it. So it's telling you how much the luminosity is pushing and the mass is pulling on our object. So it gives you some sort of energy budget sort of thingy. Well, not really energy budget, but it scales with luminosity over mass. And that's the important part here, because I want to give you some idea of what the luminosity over mass here as well, because you would expect high luminosity, low mass, a lot of outflow, high mass, low luminosity, not a lot of outflow. But it seems like the wind speed, at least, is not influenced by this at all, which is a bit surprising, but it's very similar to what other people find as well. This color bar is going to come back a lot, by the way. Color bars are now going to be usually gamma E instead if I state otherwise. Again, here, color bar is gamma E. What I'm showing here is the clumping factor, which I talked about before, over the effective temperature. And sadly, here there is no real trend to be found. It's a lot of scatter, it's big noise, not a lot to do here. You could try and compare with some modeling, some theoretical modeling, where they, from Florian Driessen, who modeled O stars and B stars, and figured out that if you use LDI, you would expect clumping factor of O stars to be about 20, of B stars about 5. These are the 3 O stars in my sample, even though they were at some point defined as B stars, but now they're O stars, so that's why they're in the sample still. Are they about 20? Maybe. The error bars are huge. I wouldn't really say so. Is this about 5? The scatter is huge. I don't really think we can conclude anything about the clumping here. More interesting is the interclump density. Because, again, scatter is really high, so this is the interclump density. It's showing you how underdense your in-between clumps is compared to average. And what you find here is, again, very large scatter, but importantly, not a scatter that wants to go to 0. You actually get really high results quite consistently. Like, again, really large scatter, because this is a log space now, so it's even bigger scatter, really big error bars as well. But you can see that there is at least not a tendency towards 0. And this is important, because if we do some fancy averaging, we get out that the average of our sample interclump density is about 0.37, with a big error margin, as you would expect. And this is completely contradictory to what these other 1D codes are doing, who are claiming that the interclump density is void. They just ignore it completely. But I get that 40% of my wind is like in these interclumps. So if you're ignoring it, you're ignoring 40% of your actual wind, which is a big part of your wind to ignore. And it's actually more or less coincides with what we see from multi-D simulations as well. What you see here is a result from a multi-D simulation. Very quickly, how it works is if you get a random parcel in your multi-D simulation, this gives you the chance of where its density is relative to average. So for instance, if I take a random parcel, you're most likely to find it at a density slightly above the average. But there is a large part of it, about 40% as it turns out, that actually is below this average. So it actually seems to agree with 2D, but again, we're not really sure if that the scatter, where it's coming from, how well we're fitting it exactly. So this is like caveats to take with it, but it is pointing to a certain direction, and it is something to look at, definitely, because this, even though we get this 40% out, this is completely not the way we do it in FOSS1. In FOSS1, we do this two-component medium, that is like two stochastic density regions, basically, while here it's more of one distribution. So it's still very different. So we're not doing it perfect either. Then we get to what I think is the most important part, which is the mass loss rates. What you see here is, again, mass loss rate of temperature, gamma E is shown here, and you see a decrease with temperature overall, and a relatively strong effect from gamma E. You see that the low gamma E's actually give you lower mass loss rates out as well, which means that this gamma E is here having some say about the thing. Not a lot, because some high gamma E's are still like very much in line with some lower gamma E's, but the actual like low gamma E's seem to have like a pretty big effect here. Now, it's difficult to say if a bistability jump is present here, even though from this you could already see that it's not really there, but you could claim, okay, but you're not taking into account mass and luminosity, and the mass and luminosity of all these stars is slightly different, so who knows where it would be on the prescription. So what I did is, I took the mass, luminosity, and so on from my fits, put them into the prescription, tried to take into account all the errors, and divided that value by my empirical found value. So now I get kind of a comparison between the two. So that means that if you're on the one line now in this plot, your prescription is perfectly telling you what my empirical mass loss rate gets as well. If you're above it, you're overestimating. If you're below it, your prescription is underestimating. And what we find is that up to this 23, 25 kilokelvin range, both prescription, both the Vink and the Birken prescription do reasonably well. The Vink prescription slightly overestimates, the Birken prescription slightly underestimates, but on average, they seem to do reasonable. But once you hit this 25 kilokelvin range, where the bistability jump occurs, the Vink rates start overpredicting by up to a factor of 100. And this is not something that large error bars can really, even though they are not really small, really get to hide, right? This is on average about a factor 50 and up to a factor 100. It's really clear that whatever this behavior is that's causing us, which is the bistability jump, is not present in my empirical data set. The Björklund rates, on the other hand, seem to follow the trend reasonably well up to 15 kilokelvin, where they drop off significantly, and then they start underestimating a lot. Okay. Then I want to quickly go over one thing I mentioned in the beginning, which is the clumping degeneracy. Very in the beginning, I said that you have this clumping degeneracy because you use H alpha, so the clumping factor and the mass loss rate are just tightly knit if you only have optical. I wanted to check if I can actually break the degeneracy. So what I plot here is mass loss rate and clumping factor, and then every dot again is a model, but now the color indicates the goodness of fit. So the lighter the color, the better the fit is. And you see this degeneracy actually present, right? You see this ellipse form that tells you that, okay, if I up the clumping factor a bit, I can reduce the mass loss rate a bit and still get reasonable fits out, but it doesn't go all the way from 0 to 50 anymore. There is like a region here that is clearly better than the rest, and this is where a pretty big but notable errors on clumping factor actually come from. This is why we can define something on clumping factor. If we didn't have a UV lines, this would just go from 0 to 50 and we would have nothing on clumping factors. So the fact that we get something out actually shows that we have at least somewhat broken the degeneracy. And then I want to highlight or reiterate how important this mass loss rate is, not only to the end masses, but all other things that have something to do with evolution as well. For instance, very recently, a student did a project on the effects of rotation on this mass loss rate effect on rotation. So what he did is he modeled a bunch of stars from, I don't know, 5 solar masses to 25, I think, and he changed the mass loss rate prescription. So he used the Vink once and the Björklund the other time, and he just looked at how, over the main sequence, the rotation rate evolves. And what you can see in the blue lines is that the light blue line tells you that the Vink rate is dropping off a lot once the bistability jump sets in, while the Björklund rate actually doesn't lose much angular momentum and therefore doesn't really slow down. So this is another reason to care about this mass loss rate, as it could influence rotation rates. If you're interested in that, for instance, for BE stars, this is something to take into account. It's not only here that we're talking about this, other papers as well, very recent papers from Joris Josiek, I think I pronounced this, where he again looked at changing the mass loss rate, not with the Vink prescription, not the Vink and Björklund prescription, sadly, but the Vink and another prescription called the Bestellener prescription, which is slightly lower than the Vink, but not as big of a difference as the Björklund prescription is. And what he saw was, again, difference in the outputs. You can see here that the pinkish ones are with the lower mass loss rate prescription, and he gets out something that he calls Wolf-Rayet supergiants, if he uses that one in the galaxy, which you cannot find if you use the Vink prescription. But it's not only in the end products you see significant differences, he also saw differences in chemical yields, surface abundance, the convection zones within the main sequence, how they behave and how big they are, all changed just by changing the mass loss rate and changing where the mass loss rate was high. So just all of this gets changed just by changing this mass loss rate parameter. And then we have a single final at the end, which looked at the SMC. That's something very similar to the last paper I talked about, but now in the SMC, and they found similar sort of results out of that. So let's go over my 2 conclusions, which is the mass loss rate that is currently implemented in evolutionary codes like MESA, but in MESA there actually is the Björklund prescription now, thanks to Matthias, so we can use the Vink prescription in there if you want, but baseline, it probably isn't. So keep that in mind, because it's probably not correct, because it's just not in line with observation. It's not only me saying that. There are other papers, the 2 papers I mentioned at the beginning, find similar results, even though they only had the upper limit estimates. And there is a recent paper on the galaxy, or like a paper on the galaxy coming out as well, that's also claiming similar things, but again, they cannot take into account clumping. So this is, again, these upper mass loss rates, but they have the same, they all see the same thing. There's no observational evidence for this bistability jump in mass loss rate at all. One small caveat here, or pretty big one actually, is that once you reach the LBV stage, there the mass loss rates get huge, and the uncertainties on those might even be bigger than the ones on the B-supergiant stage. So that's another thing to take into account. But we're also working on that in our group. If you want to know about that, talk to Peter. He probably has an answer, or we'll have some answer for you. We'll see in a couple of years if it's like a very straight answer or if it's with a lot of caveats. And then another one is that 40% of the wind, in our observations at least, seems to be in the interclump region. So if we're modeling these stars, these winds, for spectral analysis, we need to take it into account. We cannot just ignore it, and we need to improve how we do it. Because even in fast wind, we're not doing it good or perfect at the moment, because we're using this too stochastic medium, while it clearly isn't. It's more of an even distribution, so we need to rethink how we do this. Thank you.
Thanks, Olivier, for this enlightening talk. We have plenty of time for questions. Who wants to ask a question? Hans. You're actually here, Hans. Hello. I haven't seen you for ages.
Thanks for the fast talk.
Yeah, sorry.
So first, breathe. No, I have a question as well. The reason to include the jump is a reason because of the recombination. So it's an opacity that sets in at a certain temperature. Mm-hmm. But you find that you don't see the effect. Mm-hmm. That what does it mean with respect to the physical reason of that opacity being not so strong, or is there no recombination, or what is the physical interpretation?
So this recombination thing is happening. It is there. We're not I'm not saying it's not there, because it's just a temperature effect and you can check it. It's there. But what is most likely happening is that the important space of the wind, where the actual wind gets launched, the critical point, so to say, where it gets launched, in that specific region, there the combination of parameters don't allow for a higher mass loss rate. Even though the opacity is higher, it kind of gets constricted there due to its density at that specific point, that you cannot launch a stronger wind. So you can sort of think of it as there is the potential for a higher wind, but there is just not the density to drive that wind. There is nothing there to actually push it. So it's just like, it's already at like this limiting factor of how much it can push.
I have to think on that.
Yeah, it's not that easy to explain.
Hello, thanks. I was wondering, so you described your 18 parameters.
Mm-hmm.
In there were 2 parameters on the X-rays. I didn't see that you analyze X-ray spectra to derive your results. So what makes you, I mean, why did you really need those?
So I hope I left this in somewhere. Yeah, I did. Nice. So in the beginning, we didn't include X-rays because we were, like you were saying, we don't have X-ray spectra. We don't really have anything to compare to, so why include the X-rays anyway? But then we started fitting, and what we noticed is that for a couple of cooler B stars, like B4, B5 stars, which shouldn't have carbon-4 in their winds because it's just too cool, it cannot ionize carbon up to level 4 there, we needed something to induce extra ionization. We just needed something to do it, and we went to X-rays as a way to do it. And what you can see here is the difference between if we include X-rays in the red and not include X-rays in the blue, compared to the observations. And if we included the X-rays in the beginning, just as a kind of test to see what would happen, we actually are able to get this carbon-4 up without influencing any of the other lines, which is quite remarkable, and that has a big effect on our eventual terminal wind speed as well, because this carbon-4 line is the main driver, the main determinant, basically, for this terminal wind speed. So if you get that one correct, you actually get some real stuff out, while otherwise you get noise, basically, because there's nothing really to base it on. So it's more of a, at the end, adding it because we need it. We're not saying it's actual X-rays, but there's something pumping up the ionization, and X-rays seem to work.
Thanks, Olivier. So the conclusion plot you show, to me, looks really convincing. I mean, given the uncertainties you've talked about as well. But on the evolution side, will this not create like a Wolf-Rayet crisis? I mean, in a sense, it's good for us because you need more binaries to explain the Wolf-Rayets. But still, there's still a lot of single Wolf-Rayet stars. So how would you go ahead and explain these?
Yeah, no, so this is a real point. If we reduce the mass loss rate, there are certain things we see now, like single Wolf-Rayet stars, which will mostly disappear, right, if we just use this mass loss rate. Now, this comes with the caveat of the LBV. If the LBV wind is super strong, you could still produce some sort of Wolf-Rayet out there, but again, the uncertainties on these are even bigger somehow. So that could be a solution to it. The other one could be that, yeah, maybe they're all binaries. I don't know. But that is, to say it really harshly, not really a problem, for me at least, because all I'm saying is, well, for me personally, because all I'm saying is what we're seeing right now and what we're using right now just doesn't line up with reality. So that makes other things not work. That means that something else is also not lining up with reality in the MESA models, most likely. Yeah. So there is going to need to be some solution if we want to keep these single Wolf-Rayet stars alive while not tuning the LBV to some immense, the LBV winds to some immense regard. But yeah, there are like evolutionary consequences of this I have not explored at all, and there will be more than just the Wolf-Rayet one, most likely.
Yeah, for sure.
But yeah, this is all I can kind of say about this at the moment.
Okay.
More questions? Yeah, Pablo.
So I guess following up a bit on that, I guess there's also red supergiant winds that more or less you're saying something about one specific wind mechanism, but you can also have red supergiant winds that are known that they can be very strong, stripping the star. But the thing I actually wanted to ask is if you show your HR diagram with the Björklund versus others.
Yeah, in the very beginning.
It was pretty much the beginning.
Yeah. Nope, yes.
So yeah, here you have a very large difference in the two tracks during the main sequence, essentially before you're hitting your bistability jump.
Yeah.
So a lot of that translates and propagates later to produce this large effect as well.
Yeah.
So I guess my question is mostly, what is the other difference that's causing this between the Bink and the Björklund predictions?
So up to this point, the bracket I made here where the bistability jump actually becomes a thing, up to here, it's just this relatively small that is usually referred to as this factor 3 difference between the Vink and the Björklund one. And that apparently on its own already has this massive influence, just the factor 3. And it's not even talking about the factor 100 we get to later in the cooler stages. And that's all that's happening here. There's nothing, this is just, oh, the different direction. This is just this difference, basically. This like couple factors difference that you see here, and that's the only thing that's happening there.
Yeah, I'm just curious about the physical reason.
Oh, the physical reasoning. Okay, so, sorry. So the actual models themselves are very, well, not very differently constructed, but they have a different outgoing philosophy where the Vink rates themselves were based on models made that are only globally self-consistent, so the end and the beginning and end results have make sense into themselves. They have like velocities and so on, and momentum is conserved within those beginning and end points, while the Björklund rates themselves are, at every point individually, our momentum is conserved. Everything is just self-consistent the entire way through. And apparently, that produces this different behavior. There is nothing, well, nothing really else going in there. It's the same sort of base ID physics-wise. It's just the preparation of it is slightly different, the way the models have been handled, and that produces the difference in these differences in factor 2, factor 100, the bistability jump being there or not. That's pretty much it. There isn't really like a magic thing that's get added in the Björklund to get this out.
Okay. And well, I guess I always want to say a small word of caution. These variations of factor of few and wind mass loss, the effects they have on evolution are completely degenerate with uncertainties in core mixing.
Yeah.
So that's one important thing to keep in mind always, if there's large implications coming out of that.
Yeah.
More questions?
So, given your results now, in the next release of MESA, will we see the mass loss rate change, or is that still far away before we could like start changing the evolutionary codes?
So the Björklund rates are at this point implemented in MESA, so you can use them. They're not the baseline. I think for us to change the baseline, that would mean changing the perception on the field, which is going to take a long time. But my suggestion would be to already start changing it, because this isn't me just now starting to say they might be wrong. This has been going on for a while, that people have been discussing if these mass loss rates are too high, too low. People have been dividing them by 3 for a while, but I hope this plot convinces you that dividing by 3 isn't really cutting it. There's more complex behavioral changes here than just the divide by 3. But this divide by 3 has been happening, so this change in mass loss rate in the evolutionary group has been happening for a while, so I don't see why we couldn't just change to something completely different. And I'm not saying that the Björklund trains are perfect, right? They're underestimated by factor 2. After 15 kilokelvin, they seem to drop off too much as well, so they're not like the magic bullet, but up until that range I discussed, they seem to do better. So it's something.
We still have time for questions. Yeah. Okay.
So on this plot as well, there is also the blue one by Kritika or something.
Yeah, the Kritika rates, yes.
So I remember when you showed the comparison between Vink and Björklund from your data, you had that Björklund went underestimating at the lower end.
Yes.
And Vink overestimating, and the blue ones are a little bit in between there.
Yeah.
Is that a fit to the data you have, or just
No. So this is another prescription. I didn't really mention too deeply here. This is another prescription, other modeling effort, a bit more similar to the Björklund modeling effort, but some very small changes there as well, which are pretty niche. But it produces this kind of behavior that has, I don't know, not a stability jump, but a stability bump sort of thing, where it moves up a bit due to what I think are actually slightly different underlying physical reasoning. I didn't plot them. I don't have the plot with me here where I compare them to it. I did do that. The problem with this one is it is very similar to the Björklund one, actually. It seems to align pretty well up until, I can just show it here where it should be. It agrees pretty well. It's like, like you say, in between these two, so it follows this line pretty well. And then it has a slight up here where the bump happens, but here my error margins are too large to say if it's existent or not. It's very, I cannot, with the current data set, cannot say if this bump is real or not, so I decided not to include it as a way to keep this plot as clean as possible. But yeah, and the jump is also slightly cooler. It's actually not here, it's more here. And because my sample right now ends at 15 kilokelvin, I can't really explore that bump deeply at all because I don't have the observations going cool enough to see it. And my error margins in these cooler ends tend to be bigger as well, which cause it to be like constantly overlapping. So yes, this Kertészka rates could be a solution. There are some reasons to be skeptical on this one as well, just as there is on the Björklund, just as there is on the Vink ones. But yeah, this could be a solution as well.
Still time for questions, Hans.
Sorry, I have one more question. So the clumping factor is some kind of random, because you do not find a correlation with anything else, right?
Ah, yes. So there's, yes, exactly.
And can I understand that physically?
Why is it not varying with temperature or anything?
Or at least for any temperature, you have a whole range.
Yes, yeah, that's true. I think what's partially happening here is that it's just very hard to constrain, so we see a lot of noise. So if we would just be able to reduce the noise, maybe we would find something. I'm very far into. But like from modeling, we would expect it to change with temperature, right? So it's not really easy to say why it's not at the moment. If this, yeah, no, there is, like, even if it was due to some subsurface instabilities going on, those still would expect at least some variation with temperature, and we're not really seeing that either. So yeah, no, it could be due to the fact that we have some outliers and just a large noise, and it's just hard to constrain, and that's why we're not seeing anything, or there's just really nothing going on there, which means that it's mostly just, yeah, something extra going on besides from this LDI and subsurface convection that we're not really understanding why these clumps are happening. Maybe we're also too far out. We're conveying the clumping factor too far out, where it's already decreasing again in some cases. And that's why we get some noise. We actually don't know why this is so scattered.
Still time for questions. While people are thinking, so Olivier, you several times mentioned that you have this huge error bar. So what should you actually do to improve the precision of the measurements, or is this absolute best you can get?
So I think the main thing we could do, or the most likely fruitful outcome I see would be to redesign the way clumping is defined in FastWind. Go more towards we see in 2D and 1D approaches, where it's not this two stochastic medium, but like one sort of Gaussian distribution that is not averaged on 0. And if we do that, maybe we get out something better. And therefore we are, I think part of the reason why we see this big scatter is because we're just not putting in the physics correctly yet on the clumping, not completely at least. And that's part of the reason why I think we're not getting really good clumping results out yet. So improving on that side is, I think, the most likely way to solve it. I think helping here would be the 3D models. Once we get those perfect and we can trust them 100%, we can use those clumping results out and try and get them in there even better than we're doing now. We could, yeah, there's a lot of things to be changed about how we handle the clumping that might be better. I think adding extra data, because that's the other option, right? Maybe we're not using the correct spectral lines to get this out, this clumping factor. Maybe in some other range in UV or optical, there is something there that gives us the data to do this. I do not think that's going to help you much. There's just we are utilizing enough data. I don't think that's our bottleneck at the moment. Like, because in theory, we should have the information we need, but maybe our theory isn't perfect yet.
Thanks. Still some time for questions. Then I'll continue. If you go a couple of slides back on slide 27, so maybe it's me, but I sense some systematic difference between the spectroscopic masses here and what the evolutionary track dictates it to be. Can you say a few words how the spectroscopic mass is estimated and what could be the source of the difference between the two?
I'll go to a very slightly different plot I have somewhere in the back. It's just a big blob. Yes, here it is. So here I plot the spectroscopic mass and evolutionary mass, and I try to compare them. Spectroscopic mass, we have huge errors. Why do we have these huge errors? Because the way we get it out is basically defined by this log G and the luminosity. And the log G, even if you are off by 0.1, your mass changes dramatically. So that's why you get always, this is always going to be a thing, you get huge errors in spectroscopic mass. Well, in evolutionary mass, the way I did this is I used this bonsai tool, just put in my parameters, and it estimates like the mass for you, basically. So it looks at a grid around your parameters you give, and then it tries to estimate where in which evolutionary track your star should be, and then it gives you a circle around that, basically to give you the errors. And you see that the errors on the evolutionary side are less, but that is because they have to, because there's no real easy way around. They have to assume that their models are perfect, which I think most people who do evolutionary modeling would agree that none of these evolutionary models will be perfect, definitely if I'm using them out of a base grid that I just get. So these errors are most likely underestimating. So what you can see is that within the errors, we're usually on this one-on-one line, but the errors are huge. So spectroscopic mass and I think evolutionary mass equally are kind of difficult to take on face value. They give you some idea of where you're at, but they really don't. I wouldn't trust either of them, to be honest. The way you get mass out is, in this range at least, probably binaries, and that's about it.
Thank you. There is still time for one more question. Who wants to be the last? Ask any question. Then I will be the last asking a question. So on slide 34, let's see if I got the I got it right. So the 25 solar mass, Björklund dash dotted line, right? So can you enlighten me about why is the star spinning up actually?
Yeah, so how I understood it was that what is happening is that the core is contracting, it's spinning up, and it is, in some mechanism, giving its rotational velocity to the envelopes around it, due to just viscous, but also due to magnetic fields maybe, at least. There is some connection between the core and the envelope, spinning the envelope up, and the mass loss rate is too low to remove angular momentum faster than it's gaining from this spin up of the core. That's the idea behind it, and that's why it's going up. Because I was confused as well. I was expecting it to never go up, because mass loss rate is always extracting stuff, and it shouldn't be spinning up. But apparently, the connection between the core and the envelope is strong enough to actually spin it up if the mass loss rate is low enough, which I was surprised by as well.
So you're pumping up more angular momentum than you can remove, actually.
Yes.
Yeah, okay, interesting. Thank you. All right, so we are almost at the hour. I'll give 2 minutes back to of your life. Thank you for coming, and thanks to Olivier again. And see you next week.